This is not easy.
That's a good way to
This is rather challenging. Well, we're going to go slow. I'm going to show you some tricks. I'm going to talk you through it. More so than anything we've done in this class, you must get in and get your hands dirty. You will make mistakes. That's why we have erasers. If you don't make a mistake, then you're doing something wrong. But that's the nature of the beast for these problems. Simplistic terms, related rates, are word problems for calculus. We're going to be calculating all kinds of fun things. Many of them involve death and destruction. Crashing cars, falling off ladders, that kind of stuff. Oh yeah, it's going to get very metal. But we're going to start slow. I've got a 9-step approach. Yes, 9 steps that I think will help you solving these related rates. You think I'm kidding? I'm not. And oh, now I have to start over. Not kidding. I'm not starting. As you get better at related rates, which all of you will, you can start chopping out some of those 9 steps. When I was doing the problems, I'm probably down to 5 or 6 steps. I've been doing this for a while. Let's just get right after it. Hey, we're going to find a related rate. That's a rate that's related to something else. Yeah? You're going to do that using a 9-step approach. And you should be able to reduce some of your stress. This will not reduce some of your stress. Sorry. So it should say, find a different way to reduce some of your stress. Okay, here we go. Naked related rates. What's a naked related rate? That's a related rate that doesn't tie to a real world example. There's nobody falling off a ladder, crashing a car, filling a bucket that's got a hole in it, emptying a bucket that's got a hole in it, etc., etc. It's just a boring old equation. But before we get to that, we need to talk about a variation of implicit differentiation. Okay, we've been doing things like this, dy dx. So when we did implicit differentiation, you'll remember, when we took the derivative of y, we got that dy dx next to it, because you're telling the reader, I just took the derivative of y, which is not the variable I'm looking for, so I need a dy dx. All of that changes with related rates. Related rates, everything relates to time. By the way, does anybody know the reference to the picture? Okay, just checking. Good. Some of you might do well in here. Okay? So what does that mean? That means that now my variable is t. So on the left hand, we'll talk about what we did in the, whoops, or I can just click again. On the left-hand side, we'll talk about what we did before. If I took the derivative of x squared, I would just get 2x. If I took the derivative of y squared, I would get 2y dy, dy dx. That's old stuff. Now we change colors and move to the right side of the board. If I take the derivative of x squared now, I'm going to get 2x dx dt because t is my variable. If I take the derivative of y squared, that's going to go to 2y dy dt. Does that make sense? Okay, good. So you're going to have a lot of these dy, dx, dt things popping up all over the place. Yes. So the best way to do this is to dive into it using the 9 steps. So here they are. I don't know what that is. That's left over from my last slideshow. Okay, which means, hold please. This is going to be great on video. Why is that there? Don't save. Obviously, I'm going to have to do some editing now.
I suggest we it'd be funny just left it.
Okay, good. We're okay now. Got it fixed. Okay, so our first naked related rates. I just have a function, y equals x squared plus 3. It's a parabola shifted up 2. But everything in this problem relates to time. What does it mean when I say it's a differentiable function?
Take it.
Go ahead.
No, I was gonna say something stupid. I thought.
Go ahead, you're in a safe space.
No, there's a dust like definitely. I don't know.
No, I said differentiable.
I know. I was gonna say redefine it.
No,
Like,
that would be a definable
I
function.
know, yeah.
Differentiable means, what do you knuckleheads?
You can find the derivative of it.
Yeah, you find the derivative, right. You would have gotten there eventually if you weren't so freaked out by your definition. Okay, good. I'll call on you later. So we're going to take the derivative. Given some information. So you'll notice, I know that I'm looking for dy dt when x equals 1. Okay. And dx dt equals 2. So I'm just going to start with this bad boy and take the derivative. Derivative of y is 1 dy dt. We did this already. 2x dx dt. And then the derivative of 3 is 0, so it disappears. This will be fun. Bethany, how many variables or unknowns are in that equation in red?
2.
No.
No, 3.
3. Good. Basing that, what am I trying to say? Using some simple algebra ideas, if I have 3 unknowns, how many must I know to solve it? 2. Good. We'll get there eventually. 3 unknowns, I need to know information about 2 of them in order to be able to solve the problem. Well, I do. I know that x equals 1. I know that dx dt is equal to 2. Lo and behold, I solved this nice easy problem. So dy dt is equal to 4. Kelsey?
Because t is involved, you have to write it as dy over dt dx over dt. You have to write like y prime.
Great question. This implies that you're doing dy dx. So the prime notation implies that your denominator is dx for everything. So z prime would imply that you're dz dx. So the answer to your question, yes, you need to write it as dx dt dy dt. Okay. That's not a very exciting problem. But it will pop up occasionally when we take a look at these negative related rates. What we're going to do, and what's more exciting, are true related rates problems that have to deal with real-world examples. They get quite a bit more complicated, so I have a 9-step approach for you. It goes something like this. Blah, 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 blah. So yeah, okay, yeah, so then we're going to, like I said, we're going to do the people falling down ladders, and leaky buckets, and all kinds of other crashing automobiles, all that kind of stuff. Okay? So 9 steps. Number 1, draw a picture. Label your picture. Step 2, define the variables. Now, the way I solve the problem might be different than the way Sam solves the problem. I might choose X to represent some variable in the problem. Sam might choose Q. That's why you have to define the variables. So if I take Sam's problem and my problem and I give them to somebody, they can follow the problem, both of the problems, because everything is clearly labeled. Number 3, what do you know? What are you looking for? What's the given information and what is it you're solving for? Step 4, general equation. A lot of times, the first couple examples, we're going to do some geometry stuff. The general equation is given to you. Sometimes you'll have to write your own general equation. What's important there is where it says do not plug and chug yet. The only time you sub into an equation is if a value doesn't change anywhere in the problem. So notice, if I go back to this picture, when that dude slides down the wall, there's a lot of stuff changing in that picture. What doesn't change, however, is the length of the ladder. So if you know the length of the ladder, you can plug that in right away. Everything else is a variable. It changes during the problem. Okay, so where are we? We're at that. Okay. Step 5, take the derivative. That sounds like the scary part. That's actually going to be the easiest part of these problems. And I wouldn't lie to you. Simple derivatives. Step 6, snapshot. Now the snapshot means at that exact moment in time, you're going to be asked some questions. So again, let's go back to the guy falling down the ladder. A lot happens when this guy slides down the wall. I might want to know something about when he's at the top. I might want to know when he slams into the ground. I might want to know when he's halfway down the wall. That's the snapshot. It's that frozen moment of time that I'm asking questions about. Okay, so that's step 6. Step 7, solve the problem. Plug in what you know, solve for what you don't know. Step 8 and 9 seem kind of trivial, but they're important. Step 8, does your answer make sense? Most commonly, that's going to come up when you look at the value of your answer, if it's positive or if it's negative. I'll talk a little bit about that later on. You also want to look at the numerical value. If you're calculating the rate of change of your vehicle to go to grandma's house, if you get an answer like 831 miles per hour, you probably did something wrong. You're not flying in your jet at Mach 2 going to grandma's house. It would probably be something around 30 miles per hour. Now, you're going to see some problems like today that we do where you're not going to know whether or not the answer makes sense. Do you have any idea what the value is when you're filling a bucket of water? I have no idea. But again, use a little bit of common sense. If you're filling a bucket, the answer should be positive. If you're draining a bucket, the answer should be negative, that kind of stuff. And then number 3 is the units. And I'll show you some tricks on finding the units. Are you talking about miles per hour? Are you talking about meters per second? Are you talking about yards? Are you talking about the number of polar bears? Are you talking about all kinds of different types of problems we'll see? Okay, ready for this? Now, stay to you, ready for this? Okay, here we go. First one. We're going to fill a balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2. What does that mean? Well, I start inflating a balloon. The balloon gets bigger. Okay, so if the balloon is getting bigger, should the rate of change of the volume be positive or negative? Positive. Okay, those are kind of the things you want to think about when you get to the part about does this make sense? If the volume is getting bigger, what can you tell me about the rate of change of the radius? Is it getting bigger or smaller? Bigger, therefore positive. So I know that when I'm done with this problem, my answer should be positive because the radius is getting bigger. Okay. Now, as I said, the first 2 problems involve geometry. You do not need to memorize and or remember the formulas for 3-dimensional geometric shapes. You probably should know the volume of a sphere, but if you don't, that's okay. If you don't know the volume of a cylinder, you don't know the volume of a cone, you don't know the volume of a hemisphere, they'll give you all those formulas. What you do need to know is things like area of a square, area of a rectangle, 2-dimensional stuff, area of a circle, that kind of stuff. All right, so here we go. Step number 1, draw a picture. Okay, I cheated. Instead of drawing a sphere, I just drew a circle. You're with me. It has a radius of r. Step 2, define the variables. I chose to use r to represent the radius. I chose v to represent the volume. Now you might think to yourself, that's pretty common sense. Why do I have to do this? Don't assume anything. Somebody might choose m to represent the radius. I don't know why, but that's what makes this such a great country. Okay, you could choose a to be the volume because it's the air in the balloon. That's kind of silly, but again, great country. Right on. Step 3, what do we know and what are we looking for? So this is where you read the paragraph and you determine what information they're giving you in the paragraph. With the air being pumped in the spherical balloon at 4.5 cubic feet per minute, I know that that is my dV dt value. And we talked already about why that would be positive. Because it's getting bigger. Anytime a quantity gets bigger, it's positive. Anytime a quantity gets smaller, it's negative. What am I looking for? I'm looking for the rate of change of the radius at the exact moment when r equals 2. Okay, how are we doing so far? We're good? Okay. Anything not make sense yet? Beautiful. Step 4, general equation. As I said, this is a three-dimensional geometric problem, so you're not going to need to remember this. I'll give you the volume of a sphere is 4/3 pi r cubed. At this point, you're going to say to yourself, why don't I just plug 2 in for r? I know what r is. R is 2. I'm going to plug in 2. No. Why not? Because that r equaling 2 changes during the problem. It's a variable. We're going to use that later in step 6 for the snapshot, not for steps 4 and 5. Okay, so far? Step 5, take the derivative. Let's see. Alec, what's the derivative of our general equation? You guys sitting in front of you, right? I'll give it to you. Here's our equation. Take the derivative. What's the derivative of v? Q. QR.
Oh, no, it's ours cubed.
Q. Oh. Good. I was just seeing who's paying attention. Good job. You guys passed. It's amazing they let me teach geometry. Thank you. Again, I was just testing you. Good job. This will pan out really well in the video. All right, back to you, Alec. What's the derivative of v? Say again?
Just v prime.
Yes and no. We can't use v prime. That's cheating. dv over dt. Good. Derivative of v is 1, but we took a derivative with respect to time, so you stick on that to dt. Okay, good. What's the derivative of 4/3 pi r cubed?
4 pi r squared.
12 over 3 pi r squared.
12 over 3 pi r squared. You forgot something? So I'm asking you.
Oh, you can just turn it to 4.
No. We'll come back to that in a second. Lee. No, we'll do that in a second. He still forgot something.
The derivative of pi 0.
Nope.
DRDT.
DRDT. That's a constant, so it just sits out in front.
Oh.
Which is 4 pi r squared drdt. Ooh. Let's nerd out for a second. Does anybody know the formula 4 pi r squared? Do you remember what that represents? It's the surface area of a sphere. When you take the derivative of the volume, you get the surface area. That's kind of cool. Wow. That was a condescending, like, okay. Well, something for you to talk about at the dinner table. Bethany, in that equation now, let's get rid of this so you don't get confused. Okay, that's not there. We got this. How many variables? Or let me rephrase that. How many unknowns?
2.
How many?
2.
How many?
3.
3. Good. That's what I thought you said.
Yeah.
Okay. How many of those do we know right now?
0.
No. Anybody else? 2. We know 2 of them. Therefore, it should be solvable. Yes? Okay, so step 6, snapshot. This is where we look at that exact moment in time. Well, what happens at that exact moment in time? At that exact moment in time, we know that R is equal to 2. I think I can click here. Yeah, we know that R is equal to 2 and dV dt equals 4.5. Step 7, solve. That means plug and chug. When you're plugging 4.5 divided by 16 pi into your calculator, make sure you put some parentheses in there. Gesundheit. Gesundheit. Step 8. Does this answer make any sense? I have no idea. It's positive at least. I know that's good. So I'm going to go with it. I trust my mathematical knowledge. Now the units. I'll show you a trick on how to find the units. Some of you might know already. But the units of this bad boy can be found by looking at what we're solving for. We're looking for dr over dt. What are the units of the radius? Feet? I don't remember, honestly. Is it feet? Okay. What are the units of time? Is it minutes or seconds? Minutes. Done. If you're solving for dz dt, then your units are the units of z over the units of time. That will help you find that unit thing. It seems fairly obvious early on, it'll get more complicated later. How are we doing so far? Should we ramp it up a little bit? Oh, we're going to though. All right, let's talk about a conical tank. This is a picture of a tank draining. So my dV dt would be negative. The example that we're going to do on the next slide is actually going to be we're filling a tank. So my dV dt will be positive. Again, if a variable, sorry, not variable, if a value changes over time, if it gets bigger, it should be positive. If it gets smaller, you stick a negative in front of it. You'll notice that equation for a cone presents a problem. The problem is that I've got R's and H's in that formula. That's going to make things a little bit more challenging. I'm going to show you 2 ways to solve this problem. I would argue that the first one is quite a bit easier, but I'll still show you the second one just so that you see that there's other ways to solve these problems. Okay, so here's our problem. Yeah, I'll give you a second to read that. At some point as you're reading that, it will turn into a foreign language and won't make any sense, but that's okay. Try it anyways. Okay, so before we dive into this, you'll notice this, 10 gallons per minute. That's not going to work for us. So we're going to do a conversion later. Why did I put this in there? Why not just give it to you in cubic feet per minute? Because it's common practice for them to give you problems where you have to do some unit conversion. Stoichiometry? Is that what it's called? Factor label method? No? Is that something different?
Stoichiometry.
Stoichiometry, or Gesundheit bars.
Yeah.
Gesundheit bars, right? Okay, so for instance, I've got 10 gallons per minute times 1 gallon equaling 0.1337 cubic feet. Cancel, cancel, left with cubic feet per minute. Okay, we'll come back to that in a second. I'm going to leave that there just to bother some of you. You're welcome. Yeah, oh yeah, that's there. Okay, so I got a cone. It's filled with water. By the way, when you're filling cones, you can't fill an upside down cone. Nobody takes a cone off of a drinking fountain thingy jobber and turns it upside down and tries to fill the pointy side. You don't fill an ice cream cone with the pointy side up. People do it all the time, but they try in math problems, but it's an inverted cone, circular. Oh my God, I'm so excited I can't even talk anymore. Okay? Use a little bit of common sense. So there's my cone. I chose to call the radius of the water R, and I chose to call the height of the water H. I know the radius of the cone itself, because it gives that to me in the problem, it's 6, and I know the height of the cone is 12. That's a big cone. By the way, trivia question for you. You know when you're driving down the highway and you see those giant buildings where they store all the salt?
Mm-hmm.
Do you know why those buildings are cone-shaped?
The weight of the salt,
No?
so the snow goes off the road?
When you fill those buildings, it will naturally form a giant cone-shaped mound, so they build the building around the shape of the salt mound that you would get. You can't make a hemispherical salt mound. It makes it into a natural cone. Just throwing that out there. All right, let's just move on.
That makes sense.
There's my conversion. Okay, so breaking the steps down. Number 1, I drew a picture. Number 2, I define my variables. R is the radius, H is the height of the water. Step 3, what do I know and what am I solving for? I know what dV dt is. I'm going to use the 1.337 cubic feet per minute. I'm looking for dH dt when H equals 3. Step 4. Am I going too fast, by the way? We're good? Step 4, general equation. I gave you that on a previous slide. What's the volume of a cone? It is that. Sorry, I'll wait for you. We all good? Okay. Yes? No response will be a yes. There we go. There's the general formula for a cone. What do you think bothers me about that equation? Nothing. No, there's a lot that bothers me in that. Somebody said it over here. There's 2 variables in that. Does that mean I can't persevere? No, I can still do it. Bingo. That come out of your mouth? Product rule. I don't want to do product rule. Icky. So I'm going to be sneakier about it. And this is where we diverge into the 2 techniques. Technique number 2, which we'll come back to, will involve product rule. It's icky. I'm going to show you a way to do it without using product rule. I'm going to do it by eliminating one of the variables. So, next question. Which variable do you think you want to get rid of? R or H? R? Why R? Matt?
Because we know H.
Because we know H, correct. We're given information about H. We're looking for something about H. We know absolutely nothing about R. So I'm going to try to get rid of R. And I can do that, but it ain't pretty. So, boom. A little bit of geometry for you. Similar triangles. This is fun. This is a cross section of my cone with the radii and the heights. You'll recall from geometry that you can set up similar triangle relationships. How do you want to do that? You could do R over 6 equals H over 12. The radius of the water over the radius of the cone is equal to the height of the water over the height of the cone. You could do 6 over 12 equals R over H. Radius of the cone over the height of the cone equals the radius of the water over the height of the water. It's entirely up to you. You're going to get the same results. I did that last one. The radius of the cone over the height of the cone equals the radius of the water over the height of the water. Then I did some math. Cross multiplied, solve for R. Now I know that R is equal to 1/2 H. Which is good, because that will allow me to get rid of the R like we said we wanted to do. Give me a second to get caught up there, and then we'll dive into this. I'm going to do a bunch of work on the front end. By doing a bunch of work on the front end, it's going to make my derivative and the calculus a lot easier. Again, I don't want to do product rule. I can, I'll show it to you, but I'm going to avoid it if possible. So I'm still playing around with step 4, which is the general equation. Haven't moved on to a derivative yet. It looks something like this. I plugged in 1/2 H for R, and then cleaned it up. And it turns into something really nice and pretty. Pi over 12 times H cubed. Gesundheit. Gesundheit.
Thank you.
You got third one in there for a hat trick?
I don't think so. No.
Okay. Sophia, could you please tell me what the derivative of this equation is, please? I didn't hear you, I'm sorry. Love it.
And then it would be 3 pi over 12, which is 1/4 H squared.
And?
And then that would be dH dt.
Perfect. Outstanding. Let's give it up for Sophia. Bethany, how many unknowns?
Oh boy. Okay, I got it. 3.
Beautiful.
Thank
Do
you.
we know at least 2 of the 3?
Yeah.
Yeah, we know H. I don't remember what it was. Is it 2?
I believe it's
3. We know H is 3. We know dV dt, because we're filling the tank, and I told you what dV dt is. Therefore, we can solve for dH dt. Okay, good. And then that, what we just talked about, plug and chug and solve. Okay? Calculator practice. Tell me what dH dt is, please. That would involve using your calculators. As you're calculating, we're going to take an approximate answer. Remember, AP standard, 3 decimal places. Rounded or truncated, it doesn't matter. I knew you'd get there eventually, Sam.
It's
I got 15.
I feel like Harry Potter, he just kept reaching deeper and deeper into that bag.
so small.
Look at what he got. 0.189. Can somebody confirm? Got a lot of shaking heads, we're gonna go with it. Oh, I got the same thing. Feet per minute. Why feet per minute? Because H is measured in feet, T is measured in minutes. We're done. Does the answer make sense? I have no idea. Let's go with it. The height is getting bigger, so it's positive. That makes me happy. Problems? All right, put your pens down for a second. Just be mathematical sponges and follow along. I'm going to show you the other method. I would not recommend it, but I'm going to show it to you anyways, because You know how to take the product rule. Therefore, you should be able to solve it. Okay, so it looks something like this. I go back to that original equation and I use the product rule. Oh, Bethany, how many unknowns in that bad boy?
4.
Mm-hmm.
What? 6? 5.
5.
5.
dv dt, r, dh dt, h, and, oh wait, I counted wrong. 1, 2, 3, 4, 5. Right? 5. 5. Right? Good. Okay. We know dh dt, we know h, we know dv dt. We got, and so all of a sudden some variables pop up that we don't know how to solve for. So how do we find them? We have to go back to, I just cleaned that up. We have to go back to this thing with the similar triangles. You can't get away from the similar triangles. I know some of you were thinking, maybe if I use that other method, I won't have to do that stupid similar triangles, geometry thing. But no, it doesn't work out that way. Once I get that equation, then I take the derivative of that equation and I get this. You can see where this is going. Nowhere positive. Which means I know what dr dt is in terms of dh dt. I know what r is in terms of h, because I solved for that already. I know r is 1/2 h. You take all that mess and plug it in and solve, you'll get the same answer. It's just a train wreck. So, that being said, I like to do the work on the front end, get rid of one of the variables, and solve from there. We've looked at 2 different types of related rates problems. Naked related rates, which isn't very exciting, and then a geometry-based one involving some 3-dimensional figure, usually a tank, or something being filled with some air, water, oil, rocket fuel, whatever it is you're using to fill the tank. We're going to move on to the next type, which involves traveling things, cars, trains, boats, planes. But before then, I think we can take about a 4-minute break. Okay? So get up, stretch your legs, get a drink of water, go to the bathroom. I'll see you back here in 22.
Planes, trains, and automobiles.
Yes, planes, trains, and automobiles. Okay. Go there. We did that already. Yep. Okay, good. Yep. All right, now we're on a boat. I'm on a boat. Okay. This is our third type of problem involving travel of some form. Whether you've got an airplane flying over where you're standing, or you've got 2 cars heading towards each other, 2 cars traveling apart, a car heading towards a train, scary stuff like that. This is not scary. They're 2 sailboats on the ocean traveling. Please tell me you're familiar with the dirt equation. Distance equals rate times time?
Oh, yes.
All right, beautiful. That'll come in handy later. I drew a picture already, but let's clarify. I start with the ship A. Here is where A started. And then it started sailing west. Is it also safe to assume that you know north, south, east, and west?
Yes.
Good. Ship B started up here and then started traveling south. Okay, so visual, look at me here. It starts doing this. That's hard to do. Okay. The ship sails to the west while one travels south to the point where that ship started. Step 1, draw a picture. Did that already. Step 2, variables. I chose X to represent the distance that ship A travels. I chose Y to represent the distance ship B travels. Okay, so let's stop for a second. Are dx and dy going to be positive or negative? Are the values getting bigger? Is x getting bigger as time goes on?
Negative.
Getting positive. Getting bigger. Is y getting bigger or smaller? Bigger. Good. So they're both going to be positive. You can do this problem differently. I just chose to label it this way because it makes more sense in my feeble little brain. dx dt speed, or, well, okay, hold on. We'll keep it fancy. Rate of ship A. dy dt. Rate of ship B. What have I forgotten at this point? Like, I just didn't hear you. Time is already implied.
The distance between the ships?
Right. I forgot to define what I labeled as z. Z. Distance between ships. I don't know why I capitalized ships, but I'm going to go with it. Okay, that's step 2. Step 3, what do I know? What am I solving for? Okay, so I know dx dt is equal to 16 dy dt is equal to 20 what am I looking for? I'm looking for dz dt. What is the rate of change between the ships when? Well, when is 130. So what's t? Is it choice A, 30, or is it B, 1/2? Why?
Because the rate is in hours and that's 30 minutes, which is half an hour.
I don't know if you heard that, because he kind of mumbled. Say it loud, say it proud.
It's half because the rate of change is in hours and 1 to 1:30 is half an hour.
Good. Okay. Now, some problems, t is going to be 30, depending on what you're given and what information. If that was miles per minute, then t would be 30. Okay. Wow, that's a lot going on there. Okay, now the fun part, unlike the geometry problems, I didn't give you a general equation. So the question is, what's the general equation? Don't be bashful. The worst that could happen is you're wrong and we point at you and laugh till you start to cry. That's why we have counselors. I forgot I was recording. I can edit that out. We'll be fine. Mr. Reedy, could you explain this part of the video? Yeah, I don't know why our administrators all of a sudden developed a southern accent, but I can also edit that out. All right. Ellie.
Is it distance equals velocity times time?
Nope. Holy.
Distance equals rate time? Didn't you say something about d equals
Yeah, but that comes later. Now, also known as Pythagorean theorem. Come on, kids, you got a right triangle here. X squared plus 25 minus y quantity squared equals z squared. Now notice, I got a 25 minus y. Why 25 minus y? Because I defined y as the top part. So if y is how far the boat went south, then what's left to get to that starting point is 25 minus y. I assumed you're okay with that, yes? Okay. All of those things change. X changes, Y changes, Z changes, therefore I can't plug in too early. I'm going to wait on that. Step 5, derivative. Who's feeling all fancies in their pantsies? Anybody want to take a shot? Please, one at a time. Let's share. Anyone? Anyone? sometime. Dom?
2x.
It's a good start, buddy. You want to stop now while you're ahead, or you want to keep going?
I'll keep moving along.
Oh.
Next is
No.
plus.
No. You forgot something.
Oh, what is it? dx dt.
I like that better.
Hopefully, most of you.
Hold on, before we come back to you. Now you got to decide, this is one of the great things about this country is choices. So you can decide, in this great country of America, would you like to multiply out 25 minus y quantity squared? Or would you like to chain rule it?
I'm going to go with the chain rule option.
I'm gonna go with the chain.
Okay,
2.
good start. I'm going to give you the parentheses for free.
Thank you. 20 parentheses 25 minus y, and then chain on the what would that be?
That's a good question.
1. Negative 1.
Negative 1.
And then dy dt.
So close. Don't screw it up.
And then 2z dz dt.
What was that last letter?
dt.
Thank you. Way to enunciate your words clearly. Hey, let's give it up for Dom, huh? Nicely done.
I tried.
Okay, beautiful. Just to make our lives a little bit easier, be careful if you decide to do this, but you'll notice everything has a 2 in it. So now we make 2's go away. Okay. You don't have to, but
Wait, you can. That's valid.
yeah, just divide everything by 2. Welcome to Algebra 1. So you can take the derivative of that big scary formula, but you're not sure where the 2's go.
Gen Z.
Holy smokes.
Generation Z done.
Does anybody know what's coming next?
Pain. Pain and suffering.
Bethany, how many unknowns?
How many do we decide?
1. Shh. It's not 1.
No, that's one second.
6!
One
Outstanding!
Me too.
1.
Oh, Bethany,
Yeah.
of those 6 unknowns, how many do we know?
Give me a sec.
Okay,
1.
1.
4?
No,
3?
no. Getting warmer.
Okay, 2?
2. We only know 2 of 6. So what does that mean? We quit and give up. We can't do it.
Yeah.
No, I was kidding. I was kidding. Now we're going to do what's called a sidebar. What's a sidebar? A sidebar is when you move over to the side and you do a calculation that you might need to solve the problem. Hence my question about the dirty equations. Let me ask you a simple question. You're on a boat. That boat is traveling at 16 mph. You're on that boat for a half hour. How far do you travel? 8. Are we all good on that? I got some hesitancy there, and I don't know if that's because you're too cool to work with the dirt equation or you literally don't know. So let's try again. Parts Bay. You're on a boat. You're traveling 20 mph for a half hour. How far do you travel?
21. Or 10.
Oh, Tom. Okay, sidebar. X is 16 times a half equals 8. Y is 20 times a half equals 10. Everybody good to go there? Okay, now all of a sudden we go from knowing 2 things to knowing 4 things. I need one more. One more and I can solve this puppy. Where do I get the other one? You pointing at me? You get it from me? What? You get it from me?
Yes.
Okay. No.
Pythagorean theorems.
Good. Pythagorean theorem. Still in my sidebar, because I'm working in blue, I go back to this puppy. 8 squared plus 25 minus 10 squared equals z squared. Z is equal to. I'll wait.
$17.
17. Pretty answer. when you're doing your sidebars, when I did my sidebars on my homework, I'm not saying you have to be cool like me, but if you do, I highlighted it in bright green so I knew what my sidebar was. Here I changed colors to blue. So this is, again, what I call a sidebar. I went over on the side and I did a calculation that I need later. We started with a scary number of 6 unknowns. We did a little bit of simple geometry and or algebra 1, and all of a sudden we have 5 of those 6 unknowns. Therefore, it should be solvable. Therefore, step 7, solve. I'll wait. Oh, by the way, will dz dt be positive or negative? I honestly have no idea. I don't know if the distance between the ships is going to get bigger or smaller. So we'll see what happens. We'll go with majority rules. dz dt. I will give you the units though. That's going to be mph. Why would I lie to you? Why would I come over and look at your wrong answer and congratulate you and then walk away and crush your hopes later? Remember, 3 decimal places, round or truncated, doesn't matter.
This can't be right.
Something.
Helene, what do you got?
Negative 1.118 microhours.
That seems to be the general consensus. Well done. Let's give it up for Helene. Good. Okay, so what does that mean? That means the distance between the ships is shrinking at that moment of time. Maybe at 2 o'clock that value is different. In fact, it will be different at 2 o'clock. At 1:15 it would be different. At 3 o'clock in the afternoon it's going to be different. But at that one moment, that one snapshot in time, I know that that is the value of dz dt. So 7 we solved. 8, does it make sense? Sure. 9, units. We're still in miles per hour. Okay, so we're good to go. Okay. Questions on this? All right. Piggybacking on this, which is a traveling problem, we have a ladder problem. Now, let's go back to the video here, or the GIF. GIF or GIF? GIF? You go with GIF? GIF. I don't think there's a correct answer to that question. Where's my ladder guy?
It was at the very beginning of the slideshow.
Oh, there he is. Okay, so when that guy falls down the ladder, if you ask your average schlub on the street, hey, the bottom of that ladder is sliding out at a certain rate, let's say 2 meters per second, how fast is the top sliding down? Most people will say it's the same. If the bottom moves out at 2, the top has to move out at 2, or move down at 2. That is incorrect. For those of you that have physics, you probably know this.
Circle.
Well, it's the same theory as the circle. Because it's like because it's farther out, it has to move faster to come around.
I don't know how to listen to it. I don't understand that.
Watch this, here's your experience. Okay, so in that picture, what doesn't change? And I think I talked about this earlier. The ladder length doesn't change. Okay? Well, yeah, the wall doesn't go anywhere, but the value of the height up the wall does change. The value of the bottom that the ladder slides out changes, but the ladder does not change. So, let's get back to where we were. That makes sense. I saw that over there. The boat somewhere. Boats are here. No, that's the other way. Almost there. Wait, and then there's boat. No, boats. Okay, boats. We got the boats. Now the ladder. Okay, there's your picture. This one, you're on your own. Work with your group to see if you can come up with a reasonable answer. Now, I'll give you some hints before you get started. Will dx dt be positive or negative? Positive. Will dy dt be positive or negative? Negative. Good. Okay, carry on. This is early on in your related rates career. I would suggest you follow the 9 steps. I've already taken care of one of them for you. Drew a picture for you. You're welcome.
Was like the distance between the wall and the ladder.
Yeah. Horizontal distance.
Yeah, but
Why?
all I know is dx over dt equals 2, and then the ladder is 1 feet above y is y.
And then dx dt. Did you solve it? dx dt is the horizontal velocity, right? Speed.
Okay, let's talk about this. Most groups got the answer, so I don't want to take it from start to finish, but you'll see that we can go from something fairly simple like a Pythagorean theorem problem to something a lot more complicated like this silly ladder thing, which I can't get my clicker to work. There are a lot, the problem with, well, there's a lot of problems with related rates, but one of the problems is that there's a lot of opportunities to screw up on. Okay, so small things like a minus sign can completely change the answer to your problem. Therefore, you need to be careful when you're doing that. So for instance, in this problem, we talked already, dx dt is a positive value because as the problem progresses, this value is sliding to the right. But this value is sliding down, so therefore the value is getting smaller. Since y is getting smaller, dy dt should be a negative answer. By the way, from what everybody told me, dy dt is equal to negative 2.667. Yeah, feet per second. Okay. Identify your variables. What's x? X is the distance that the base of the ladder is away from the wall. What's y? The height up the wall. dx dt is the rate at which the bottom of the ladder moves. dy dt is the rate at which the top of the ladder moves down. You don't need to define the 20 because we know that's just the length of the ladder and that's not a variable.
Oh yeah, that makes sense.
Your general equation is x squared plus y squared equals 20 squared. A number of you made the following mistake. What did I do wrong? The derivative of a constant is 0. Be careful with that. 4 unknowns. I know 3 of those. I'm sorry, I know 2 of those. I got to go find the other one. So this one involved a sidebar coming back to the problem, plugging 12 in for y and solving for x to get 16. Then plug and chug and solve. Okay? Questions? All right, now let me talk a little bit more about related rates. These are one of the more challenging things that you're going to have to deal with in this class. However, as you practice them, you'll get better and better. There are going to be some that, like I said earlier, you're going to read it and it's going to seem like it's written in a foreign language. Break it into parts. That's why the 9-step process is there, is that it should theoretically simplify what you're doing. I will take very few of these problems helping you from start to finish. We're gonna spend a lot of time on related rates, and we're gonna spend a lot of time with me helping you set it up, or answering small little tidbits of information versus going from start to finish. There's not a lot that I can help you with if you just watch me do the problems. So again, get in and try these problems. Get something. Get to a general equation. Take a derivative. You'll screw up on some things. Part of the challenge is going to be where you screwed up, finding that and correcting it. Okay? We good?